So let's see, we've been talking about root systems. Last time I proved for you this very important theorem that says that basically root systems and Coxeter groups are almost the same thing, in the sense that if you have we knew already that if you have a Coxeter system, then from it we could build a root system. So we knew this already, and what we learned last time is that this goes the other way also. So if you have a root system, then you can build a Coxeter system out of it. And the reason that I make these arrows separate is to make it clear to you and remind you that this is not a bijection. There are different root systems that give rise to the same Coxeter system. But the important thing is that every Coxeter system arises in this way. And so basically we can prove things about Coxeter systems or root systems and go back and forth. So let me prove an important proposition, which basically says that finiteness is preserved under this map. In other words, a Coxeter group is finite if and only if any of its root systems is finite. So how do we prove this? Well, first let's go forward. So let's start with a finite Coxeter group. Well, we know that the roots in the root system correspond to the reflections in the Coxeter group. Now, maybe I should give you I should say a word about this, because we proved this when we started with the Coxeter system and constructed the root system out of it. Okay? But like I said, there's different root systems for the same Coxeter system. And so really to use this, you kind of have to start with the root system and convince yourself that still, for any root system, the roots in the root system correspond to the reflections in the group. But if you think about how we did this in the original case, then the proof is exactly the same in this case. Okay? And once we have this correspondence, then it's clear that the number of roots is finite, because W is finite, and so it has finitely many reflections. Okay? So that direction is easy. The other direction, we have to do a little bit more work. So let's assume that phi is finite. Okay. Now, what I want to do is the following. Remember that an element of the Coxeter group permutes the roots around. Okay. So each element of my Coxeter group permutes the set of roots. Okay. Now, what I claim now is that each element permutes them in a different way. In other words, you cannot have two group elements that give you the same permutation of the roots. So these permutations are different. And the way I'm going to do this is by supposing that this is not true. So suppose that we have W1 and W2 elements of the group, which do the same thing to the roots. Okay? So what W1 of beta is equal to W2 of beta for all roots beta. And what I want to conclude is that actually W1 and W2 are really the same group element. Okay? Well, I just do the following. I say W2 inverse W1 of beta is equal to beta, right? Just by multiplying on the left by W2 inverse. And what that means is that W2 W1 takes every positive root and leaves it alone, so it leaves it positive. So this is positive for all beta positive, right? Because this is equal to beta. But then the thing is that, well, in particular, this is true for the generators. Okay. For all the simple roots, W2 inverse W1 of the simple root is positive, but we know what it means for W2 inverse W1 to be positive. In fact, just to be consistent with the previous notation, I usually call the simple roots alpha i's. So let me put alpha I here. And then I know that I have a way of restating this, which is that the length of W2 inverse W1 SI is bigger than the length of W2 inverse W1 for all generators SI. Okay? And so what do I have here? I have a group element that gets longer when I multiply it by any generator. And we know what that element must be. That element must be the identity. It's the only element that gets longer when you multiply by every generator.
Is it also appropriate to say that since it permutes all the simple roots, then it must be the identity? Because if it took one of them into negative, it would make it negative. Is that not true? Wouldn't know if it were not the identity? Wouldn't it make one of the simple roots negative?
Yeah.
Wouldn't it make one root negative?
Yeah. So let me write the conclusion, and then I'll repeat what you said, which is also right. We have a group element that sends all the positive roots to positive roots. Okay? But how many positive roots become negative? Well, we know that that's the length of the element. Okay? Here, no positive roots become negative, which means that the length of this element is 0, which means that this element must be the identity. So that's Andrew's argument, and that's maybe even better than mine. So I conclude W1 is equal to W2, which is good. So that's what I wanted to show. These permutations are different. Okay. So what did I do? Basically, for each group element, I have a different permutation of phi. How many permutations does phi have? Well, phi factorial, the order of phi factorial. That means that the order of W has to be at most the order of phi factorial, because for each group element I have a different permutation, okay, which is finite. Which is what I wanted to show. Okay. So that proves to me that finite Coxeter groups correspond to finite root systems. Now, why do I care about this? I should tell you. I mean, in general, it's a nice thing to know. But the reason that this is very important, let me write it here, is that our next main goal in the class, I forget if I told you, but our next main goal in the class is to describe all the finite Coxeter groups. Okay. And by this proposition, it's equivalent to describe all the finite root systems. So this is good, since our next goal will be to classify all the finite Coxeter groups. Now, this might be the first class where you hear this word classify. So what do I mean when I say classify? I mean what biologists do. They want to study mammals, and biologists basically like to have a complete list of all the mammals that exist. Okay? We're studying Coxeter groups, and what we want to do now, we want to study finite Coxeter groups, and what I mean by this is we're going to make an encyclopedia of all the different finite Coxeter groups that exist. And it turns out that it's possible to do this. A priori, we don't know if this is a hopeless question or not, but it's a nice fact that we can classify them so we can describe exactly which ones are the finite Coxeter groups. Okay? Which is what we'll spend the next few classes doing. So before we manage to get there, I want to tell you a little bit about a very nice family of root systems called crystallographic root systems. So I'm going to say that a root system phi, comma, delta is crystallographic. By the way, let me go back to this point here. This friend of mine was just in the news because he discovered a new bird. Okay, this is not going to happen for finite Coxeter groups. So we're more demanding than biologists in that we want to classify all of them. I don't want to just give you the list of all the ones that we know. We're going to be able to really say exactly what the finite Coxeter groups are, and no one is ever going to discover a new finite Coxeter group that we didn't know before.
So there's no Darwinian evolution of Coxeter groups.
That's right. There's no evolution of Coxeter groups. They are what they are. So a root system is crystallographic if the following is true. This is going to be a strange definition, but I'll tell you why it's important. We keep seeing this number. It appears in all our reflections. This is the number that appears when you do rho sub alpha of beta. Now, rho sub beta of alpha, when you reflect alpha with respect to beta, this is the number that appears. And a root system is crystallographic when this number is always an integer. So for every pair of roots alpha and beta, first of all, remember that roots have beta comma beta positive. This is not 0. But we're going to demand that this number is an integer for every alpha and beta. And if so, we call the root system crystallographic. Now, normally we like to write this in a slightly different way by saying that for each root beta, let me define something called beta check. So you read this, beta check. And beta check is just the following renormalization of beta. So it's beta multiplied by -2 and divided by beta comma beta. So this is just beta times a number. Okay, beta check is just some rescaling of beta. And so if we do it this way, then we can write this a little bit more cleanly as alpha beta check is an integer for all alpha beta in phi. Okay. So this is our definition of our crystallographic root system. Okay. So before we say much about this, let's talk about an example, which is this example that I drew when we first started talking about root systems. Okay, this is a root system for, I told you, the hyperoctahedral group S2 of B, which we also call B2. 2b. Okay. So remember that we talked about how this was a root system, but we saw how this root system has two orbits. And what I meant by that is that if you let the group B2, so if you let the group B2 act on these roots, then all the short roots are always going to go to the short roots, and all the long roots are going to go to the long roots. And what that allows me to do is that it allows me to rescale these four guys in one way and these other four guys in a different way and still get a root system. And I told you that I wanted to draw it like this, where this was kind of inscribed in a square here. Okay. In other words, the choice that I wanted to make is that my roots were E1, E2, E1 plus E2, E1 minus E2, and their negatives. Okay. The reason that I wanted to do this is to make this crystallographic. So let's check that this is crystallographic. First of all, what is E1 minus E2 check? Well, it's minus 2 times E1 minus E2 divided by E1 minus E2, comma, E1 minus E2. Okay. Now, the inner product of E1 minus E2 with itself, we get a 2 here. And so we get minus E1 minus E2, which is E2 minus E1. Okay. So that's this guy check. Now what about E1 plus E2 check? Well, you can see that all I have to do is put pluses here, but the answer is basically the same. Just switch the minus to a plus. Okay. What about E1 check? Well, it's minus 2 E1 divided by the norm. In other words, what we get is minus 2 E1. E2 check is minus 2 E2. Okay? So, and what about the negative roots? Well, for the negative root check is equal to just changing the sign of what you get here. Okay? And so if I want to claim that this is crystallographic, what I would have to check is that this thing, this thing, this thing, and this thing give me integers when I take inner products between them. But you look at it and it's perfectly clear because this is really the Euclidean inner product and all you see is integers. Okay? And so this is a crystallographic root system. Now think about what would have happened if we didn't renormalize. And we just let these be the usual roots on the circle, and these guys would have length 1 instead of length root 2. Well, what would happen is that when you go ahead and do this procedure, you get these root 2s. Okay? And so by renormalizing and making this a little bit longer, I managed to make these numbers integers, which they wouldn't be otherwise. And that's why I like this renormalization. So doing this, we managed to make this root system crystallographic. Okay. Now, why this strange definition? Why do we care about crystallographic root systems? Well, this goes back to a bigger question, which is why do we care about Coxeter groups? Okay. And let me tell you one of the main reasons that people care about Coxeter groups. Is that they play a very important role in the theory of what are called Lie groups. So let me just tell you very, very, very roughly in a couple of sentences what this is about. A Lie group is a group that is also a differentiable manifold. In other words, it's some kind of object where you can do algebra and you can do analysis at the same time. And the algebra and the analysis are compatible with each other. That's basically what the theory of Lie groups is about. So when you hear this classification of people between algebraists and analysts, don't believe it. Or try not to believe it, or try not to be one of these or the other category, because it doesn't make sense to put mathematics into little boxes. Really, it just comes together, even if you don't want to. What's an example of somewhere that you can do algebra and analysis? For example, Rn. Yeah? Rn has a group structure. You can add, you can rescale, but you can do analysis in Rn. Or for example, invertible matrices. You can do both algebra in invertible matrices, the group of invertible matrices, but these things also have a manifold structure, which is differentiable. It's very nice. And so these are two examples of Lie groups. Okay. Now, Lie groups can be manageable or not manageable. And so the nicest family is what is called compact Lie groups. And if you have taken topology, you know what that means. If you haven't, just think that these are a nice family of Lie groups that people would like to understand. And let me add some other adjectives here. Simply connected compact Lie groups. Okay, so again, if you know topology, you know what these adjectives mean. If not, just think that this is a nice family of Lie groups. And the very nice thing about these Lie groups is that even though they're these very big structures, definitely not discrete, it turns out that basically, even though these guys are very big, they're kind of encoded in Coxeter groups. Okay? And a lot of the theory of Coxeter groups was developed to understand these things. Okay? And it just turns out that if you want to classify these things, and this should seem like a pretty hopeless question to you, to classify the things, the objects where you can do algebra and analysis. This should sound like a very hard problem to you. These hypotheses are not so restrictive. It doesn't sound like it. But it turns out that these things are exactly in bijection with, well, these things are basically the same thing as crystallographic root systems. Okay. If I say isomorphism classes of, then this is really a bijection. Okay. And so this is why we want to understand crystallographic root systems, because if we do, then we will understand these objects. Okay. And so this is just a definition that comes from the Lie group theory, and it's what we have to deal with. Okay. So that's that. So
rephrasing this definition of crystallographic root system in terms of like a lattice basis or something.
Yeah. So we'll see that basically what you want here is kind of a lattice structure on your roots. I'll say something to that effect. So here's one example of a crystallographic root system. Another example is for the group AN-1, which is the symmetric group. Now, so I should tell you that so far in the class I had been calling the symmetric group Sn and the hyperoctahedral group SNB. And people also like to give them the names B2 and AN-1, and we will see why. Okay? Just want to start giving you this thing, this name. We talked about how a root system is given by the vectors of the form EI minus EJ. Okay. And well, we already computed what EI minus EJ check is. It's just EJ minus EI. And therefore, if you take the inner product of one of these guys and one of these guys check, again, you only see integers, so you're going to get an integer answer. Okay. So this is a crystallographic root system. Okay. And I guess in general, I talked about how for SNB, a choice of root system is given by EI minus EJ for I. Sorry, this is I different from J. They don't have to be in order. Okay. EI plus EJ and EI. And again, you can see that the argument that we made here works in exactly the same way to show that this is a crystallographic root system. Okay. So these are some examples to have in mind when we prove these theorems about crystallographic root systems. So here's a nice fact. Let's suppose that we have a root system, and we would like to know whether it is crystallographic or not. Okay? So to check that, what we would have to do is check the inner product alpha beta check for all alpha and beta in phi for every pair of roots. But it turns out that it's enough to only check it for the simple roots. Okay. And if for the simple roots it's true that these inner products are integers, then it will be true for all pairs of roots, and this is crystallographic. Okay. Which is very good because we know that phi can be a lot bigger than delta. In other words, if we look at this example over here, it would have been enough to just check that the inner product of E1 minus E2 and E2 is an integer, that the one of E2 and E2 check is an integer, and that E1 minus E2 and E1 minus E2 check is an integer. So we only have to check 3 things instead of doing it for all the possible roots, which I guess is 64 things. Now the other thing is basically what Aaron is saying, that if you have a crystallographic root system, then all your roots land on the lattice generated by the simple roots. So they're not just real combinations of the deltas, they're actually integer combinations of the deltas. And this is an if and only if. You can easily check. So if you're not so happy with this definition, you can think that a crystallographic root system is one where the roots land on the lattice generated by the simple roots. That's equivalent. Okay? So proof B is easy because, look, every time that you take, what is an element of phi? What does it look like? Well, it's a group element times a simple root. Okay? So group element times simple root. Okay? But what is a group element? A group element is, it can be written as a word in the generators. And what are the generators? The generators are the simple reflections. So I don't know, simple reflections sigma A, sigma B, up to sigma C, I don't know. And the thing is that when you look at what something like this looks like, I don't know, sigma alpha j of some root, it's beta minus 2 times this number, alpha j beta over beta, over alpha j, okay? And the point is that this number that we see right here is an integer, okay? And so what we get is that when we reflect beta with respect to alpha j, we get beta plus some integer multiple of alpha j. Yeah, sure. Okay. So you start with the simple roots, and when you start reflecting with them around, with every reflection, all you get is integer coefficients. And so all of phi is going to be obtainable in terms of integer coefficients. So that's that. And that's kind of the point, again. I mean, the point is that these are the numbers, these are the coefficients that appear. Okay? And our hypothesis is that the coefficients that appear are integers. So it shouldn't be a surprise to you that we're only going to get integer coefficients. That's kind of the definition. Now, what about A? So let's suppose that alpha beta check is always an integer for simple roots. Okay? So let me make a claim. Okay? My claim is that actually, let me do this a little bit differently. So let me prove that this is an if and only if. Okay? If and only if. And then we'll delay this for a second. So we already proved one direction of this statement. Now let's prove the other direction. So suppose that phi is of this form. Okay? So what do I want to do? I want to say that I get something crystallographic. See if I'm ready to improvise here. You know, let me just not improvise. Let me just do it the way that I wanted to do it. Sorry about that. So the way that I wanted to do it is basically the same. I'm going to assume this. Okay? I'm going to assume that for simple roots, these inner products are integers. Now, what I want to prove first is the conclusion of part B. Okay? And then after that, I'll prove that I can return. So this is what I have. What do I need to check? I need to check that a root in phi, which I can think of as a group element times a simple root, is an integer combination of the simple roots. Okay? Now, it's enough to prove this for the generators. So I want to show this for all of W, but it's enough to show it for the generators. Why? Because if every time you introduce a generator, you only introduce integer coefficients, then you can introduce several generators and only integers are going to appear. Okay? But what is this? Well, this is alpha minus, again, 2 times blah, blah, blah. This is the same thing as alpha and alpha I check. Alpha I. Okay. That's the definition of sigma I alpha. And by hypothesis, alpha is a simple root and alpha I is a simple root. So that means that this is an integer. And I have an integer combination of alpha and alpha I. So that means that I have that. Okay. So now, given this, I want to prove that this implies my group is crystallographic. My root system is crystallographic. Okay. So now, what I need is that my root system is crystallographic, meaning the definition. Gamma, comma, delta check is an integer for gamma and delta in not just the simple roots, but all the roots. That's what I need to check. And the way I'm going to check this is the following. Again, delta is some root, which I can write as w times a simple root. Okay. Now, let's figure out what happens to delta check when I write things in this form. Okay. Delta check is w times alpha check. By definition, this is minus 2 w acting on alpha divided by inner product of w acting on alpha and w acting on alpha. Okay. But again, remember that the group acts in a way that it preserves the inner product. So if I have w on both sides, I might as well not have it, and I'm going to get the same answer. Okay. And the action of w is linear, which means that I can pull w out of here and get this. Okay. And what I get is that this is w acting on alpha check, which is what you might have expected, or what we might have hoped for. That it's basically like when you do a check, w just doesn't even notice. Okay. So what does that mean? We have to compute gamma, comma, delta check. This is the same thing as gamma, comma, delta check is w acting on alpha check. Okay. Where now alpha is simple, so we like that. Now again, the action of w, the action of the group preserves the inner product. And so that means that I can make w inverse act on both sides, here and here, and I'm going to get the same inner product. So I get w inverse of gamma and w inverse w of alpha check. But of course, this disappears. And what do we know about this? Well, what we know about this is that we have some root and some group element acting on the root. Okay? So that means that this is some root in phi. Okay? But we already proved that phi is a subset of z delta. Okay? So that means that this is an integer combination of simple roots. Okay? So in fact, let me just write this out as integer combination of simple roots. Okay? But again, the point is that we have linearity here, which allows us to do the following. This is what we get because this is a bilinear form. And then what you see here is integers, right? Ci's are integers, and alpha I comma alpha check are integers because the alpha i's and alpha are simple. So this is integer, and we're done. So that proves my proposition. Let me leave this up. Let me leave the proposition up. So, by the way, you see we proved this is an if and only if because what I did is I started with this claim, and from that I proved that I was crystallographic. So I did prove that this was an if and only if. Okay, so this is good to know. I want to use the first part of this proposition now to do something. So let me leave this part alone. Because what I want to do is the following. I want to given a root system, I want to encode the root system in a matrix, which is called the Carton Matrix. Okay. And the Carton Matrix is what you get. Cartan Matrix, I guess is the right way to say it. The Cartan Matrix is basically what you get by computing these numbers. So it's a matrix where the rows and columns are indexed by the simple roots, and in the entries you just compute these products. Okay. So let me write it in symbols, and then we'll do an example. So the rows and columns are indexed by the simple roots, okay, and the entry alpha comma beta is just this number alpha and beta check. Okay. So why don't we compute some Cartan matrices here? So Cartan matrix here is labeled by the simple roots, right? So E1 minus E2 and E2. So it's a small matrix, 2 by 2 matrix, and I just compute the inner product of this thing and this thing check. And maybe it's useful just to remind ourselves that if you put, let's just put the root check up here. So this is E1 minus E2 check, and this is E2 check. Okay. I'm sorry? Oh, minus 2E2, which is E2 check. And so I compute inner product. So E1 minus E2 and E2 minus E1. What do I get? I think I'm off by a sign here, but it's minus 2, right? I mean, remember, E1 dot E1 is 1, E1 dot E2 is 0. So what we get is minus E1 dot E1 minus E2 dot E2. Okay. Now, here, I get the inner product of this and this, which is 1. This and this is 2. And this is minus 2. Okay. And so this is the Cartan matrix of this root system. What does it look like for this root system? So what are the simple roots? Remember, the simple roots are EI minus EI plus 1. Okay. So they look like this. Well, let's do it for S4, and you'll see the general pattern. Okay, so this is a 3 by 3 matrix. Again, let's just put the root check above the root. So just to make sure you understand, so what I'm writing in green is alpha check, right above alpha. Okay? And I take the inner product of this, and I get minus 2. This and this, I get minus 2. So this is what I get in the diagonal. Now, E1 minus E2 and E3 minus E2, well, basically the E1 and the E3 are not noticed, and all you get is the minus E2 and the minus E2, so you get a 1 here. Okay. And again, if we do this one, it's this E2 and E2 give me a 1. If I do this one, this minus E3 and this minus E3 give me a 1. If I do this one, this E3 and this E3 give me a 1. And what about these two? Well, E1 minus E2 and E4 minus E3 are perfectly orthogonal, so I get a 0. And E3 minus E4, E2 minus E1, I get a 0. Okay. And hopefully you see the pattern that would emerge if I do this for bigger values of n. You know, E1 minus E2 has these, still this minus 2, this 1, and now it's going to be orthogonal to E3 minus E4, E4 minus E5, etc. Okay. So what you're going to get is minus 2, 1, and zeros, etc. And so if I wanted to do this for Sn, the Cartan matrix is given by minus 2's in the diagonal, 1's in the diagonals above and below that, and zeros everywhere else. Okay. Let me just make a quick remark that if I know the Cartan matrix, for delta, then I can recover the whole root system. So let me say if I know delta and the Cartan matrix, then I can recover the whole root system. So why is that? Well, let's see. We know these numbers. We know the simple roots, and I want to compute every root. Okay. Now, of course, if I want to compute phi and delta, well, I said that we know delta already, so all I need to know is what phi is. Okay. And the way that you get phi from delta is by acting on the group, right? So the point of the statement that I'm making is that from the Cartan matrix, you understand how the group acts on the simple roots. So let's see that. Step 1 is that I know the following. I know what a simple root, what a simple reflection does to, well, let me put it this way. If alpha and beta are simple, then I know what this is. I know what a simple reflection does to a simple root. Why? Because this is beta minus beta comma alpha check alpha. Okay. So if alpha and beta are simple, then I can just look up this number in my Cartan matrix, and I know what it is. Okay. So that means that for any simple root, I can compute the simple reflections acting on it. Okay. that means that I know what sigma alpha of V is for any combination of simple roots. Okay? Because I know what it is on the simple roots, and I know that sigma alpha is a linear operation. Okay? So what that means is that I know exactly how the simple reflections act on, sorry, this is not even Z, just the span of the of delta. Since I know what sigma alpha does to delta, I know what sigma alpha does to the span of delta. Okay? Now, if I know this for each individual generator of my group, then composing that, I know what the group does. Okay? So I know what W does to V for any V in the span of delta and any W in the group. Okay? But that means that I know what the group does to the simple roots. So that means that I know W on alpha I for each simple root, which means that I know phi. Okay. And it would be good practice for you to, for example, look at that Cartan matrix of S2B, and just from that Cartan matrix, so I give you my simple roots. I give you that the simple roots are E2 and E1 minus E2. I give you the Cartan matrix. It's a good exercise for you to, from that data only, and without looking at a geometric picture, figure out that this is the root system, that everything is like here is in the root system and nothing else is in the root system. And so that means that crystallographic root systems are in correspondence with integer Cartan matrices. And so if we want to understand crystallographic root systems, then we should understand what an integer Cartan matrix can look like, and that will be what we will do next time. Okay.
So, I've always hear about